Now I'd like to show you how you can implement the Karplus-Strong plucked string algorithm in LabVIEW. The heart of the algorithm will be the digital filter, and we use the so-called IIR filter structure. This filter requires two sets of coefficients, those called the reverse coefficients and the forward coefficients. Let's take a look at the actual equation being implemented by the LabVIEW filter itself. If we compare what we see in the help file to the difference equation that we've derived for the Karplus-Strong algorithm, we can then begin to compare the coefficients and see what we need. So let me begin by writing it in the same similar form, and observe that if A naught is 1, the equation starts to look more like what we see in the LabVIEW help. Here we see that the B coefficient is associated with the input x. Now let me change the signs to match the sign on the summation. We see that we'll have a long string of zero-valued coefficients until we finally get out to capital N. So all of the intermediate coefficients A1 through A sub cap n minus 1 would be 0. A sub n would be minus g, and A sub n plus 1 would also be minus g. Now our vector of so-called reverse coefficients, A is the reverse coefficients, would look like 1 whole string of zeros and 2 minus g's. Intuitively, kind of think of that as constructing the delay line, that big gap, and then we see our low-pass filter happening at the tail end. B is the so-called forward conditions, and it just has one element. I'll begin by placing some front panel controls. F naught would be the desired pitch. F sub s is my sampling frequency. And the total duration of the waveform, I'll call that dir, or dur, also in seconds. My loop time will be the reciprocal of the desired frequency, and loop time has unit of seconds. The reciprocal of sampling frequency would be my sampling interval. I'll call that dt. That would also have units of seconds. If I divide my total loop time by the sampling interval, that gives me the length of the delay line. So that's what we've been calling capital N. Let's just take a quick peek at how we're doing so far. I had a temporary indicator there. Yeah, if we tried something like, say, 440 Hertz, concert A, and a sampling frequency of something reasonable like 10 kilohertz, we see that the result is 22.73 or 7273 and so on. So we need to make this become an integer before we can work with it much farther. And what I've done is essentially lopped off the fractional part and just retained the integer part. Let me next work on forming the input signal x of n. I'm using the white noise source. Simply give it the total number of samples required. So that value of n samples for the white noise is essentially the beginning of the pulse. I then need to add on a vector of zeros for the duration of the signal. Again, let me make sure that overall I'm creating an integer number of samples. Next, I can join my vector of silence to the white noise pulse. And actually what I'm doing specifically is replacing the first n samples with white noise pulse. I'll just take a look at that. Well, it helps if we have a non-zero duration, so let's do that. 0.5 seconds. If you look carefully at the beginning of the graph, you can see the pulse. Here, let me shorten the duration so you can see that a little better. Let me change its label to x of n, and we'll keep that graph handy. Now the filter has its input excitation. We still need to generate the coefficients a and b. I'll just go ahead and create the output display graph, and we'll label that y of n. Our filter coefficients require that low pass filter value g. I'll just set that to 0.4 for now. What I'll do next to set up the A coefficients will be to use the build array element. So if you recall, and you can scroll back earlier in the video if you need to see this, but the A0 coefficient is 1. I then need n I think that's n minus 1. Or that is, we need our A1 through our an minus 1 coefficient to be 0. So I'm creating a subvector of all zeros here. And it does work out to be n minus 1 samples, if you think about that. It was A1, A2, so on and so on, up to an minus 1. So a total of n minus 1 samples. Then I need to form minus g. Actually, the subtracting 1 doesn't help. I need to change that to the change sign node. And if I do that 2 times, now I've got my A vector ready to go. Let's just take a quick look at the numerical values to see how we're doing. I see we've got a broken arrow for some reason. What's happening here? Oh yeah, build array still has too many input terminals exposed. Let me shrink that down by 1. Now n is pretty long, so that's why we're seeing all of the zeros there. Let me make the pitch higher, which gives us a shorter n. And I'll actually put down an indicator for n. Let's stick that over here, try rerunning. I just want to confirm that we do in fact have the correct number of zeros here. N is 11. And when you count that up, you see that we've got 10 zeros in a row. Everything looks good, and I see my minus 0.4 showing up 2 times at the end of the vector. Now the B vector, that's pretty simple. It's just a value of 1. You could possibly just attach a constant 1 to this. I haven't experimented with that. What I'll do instead, though, is use the same build array technique that I did for the A vector, but I'll just do the single element of 1. Alright, now we're starting to see some interesting output appearing at y of n. Let me go ahead and put this back to some little bit larger values of n, which will prolong the resonance of the string, or the oscillation time of the string, so to speak. I'm going to zoom in a bit so we can compare the front end. Here we see the noise-like character of that initial noise pulse. And if we look somewhere in the middle, we see that it's almost totally sinusoidal at that part. It's kind of a distorted sine wave, so that tells us that we still have a little bit of harmonic content. More towards the initial transient of the note, we see even more harmonic content. And this is kind of fun. You can simply scroll through the waveform and compare it at various points in time as well. Alright, this looks pretty good. There is one issue though. If we consider the final steady state value, you'll see that sometimes it's not always right at 0. Here we see that it kind of started low and it starts converging towards it. And what I'm doing is just simply running it, and each time it has a little bit different random signal for the initial pulse, and each time you end up at a slightly different DC offset. Turns out that what we need to do is make sure that the noise pulse has 0 average value before we apply that to the filter. Having a non-zero value means that at the end of the waveform, when you actually do in fact shut it off to 0, you hear kind of an annoying click out of that. What I'm doing here next is considering the normalize sub VI. Now you'll notice that the output ends up being noticeably more than just plus and minus 1. Kind kind of a workaround here, I suppose. But this works, actually. What I'll do is simply use normalize to calculate the average value, and then I'll subtract that from the noise pulse. That way I can ensure that my maximum value is always limited to 1. Well, let's take a listen to this. I'll use the play waveform express VI. And play waveform needs the signal array to be formatted as a waveform. And dt is my sampling interval. And here's my signal. Alright, let's take a listen. Sounds pretty good. Again, longer or larger values of G give you longer ring times. Let's make an even longer delay line. That sounds pretty good. Let's try a little bit better sampling frequency next. 10 kilohertz is rather low. Here's CD quality sound. That's kind of a very metallic character to it. Remember that 0.5 was the maximum for stability. Let's try a little bit larger. If you listen carefully, you can hear how it gradually gets louder. And again, we try to limit that to 0.5 since we see that when it goes unstable, the value rapidly goes beyond 1. There you have the basic Karplus-Strong pluck string algorithm as implemented in LabVIEW.